There are images that show us beauty, and there are images that show us truth. This one does neither. At first glance, it looked like a failure, a photograph that refused to focus, but behind that blur was something extraordinary. The third interstellar object ever observed, 3I Atlas, currently racing through our solar system. What does this mysterious image actually reveal? What secrets are hidden in the data that our eyes can't see? Let's explore this together.
Chasing motion.
How do you photograph something that refuses to stay still? Capturing 3I Atlas wasn't like shooting an ordinary comet. It moves too fast and shines too faintly for any normal exposure to work. By the time a telescope collects a few seconds of light, the object has already traveled thousands of kilometers, moving at a blistering speed of roughly 12 kilometers per second relative to the sun. A single frame would show nothing but a soft, meaningless streak. To overcome that, as orbital dynamics expert Davide Farnochia can attest, the telescope had to chase it. Tracking software predicted the comet's path second by second, adjusting the mount in near real time to keep the magnitude 17 object perfectly centered on the sensor. For context, that is over 25,000 times fainter than the faintest star visible to the naked eye. As a result, the stars in the background blurred into trails, but 3I Atlas held its position. What looks like a still blur in the final image is actually motion perfectly cancelled out. The challenge is immense. Even a tiny error in the predicted trajectory would smear the object into invisibility. This wasn't just a photo. It was time made visible, a precise balance between the comet's impossible speed and the telescope's relentless pursuit, a feat of engineering that astronomers at the Minor Planet Center work to perfect daily.
Shape without surface.
What do you do when an object's shape is also its shadow? In the image, 3I Atlas doesn't show a surface. There's no crisp edge, no nucleus shining at the center. What we see instead is an outline that refuses to stay defined, a gray body that fades into itself. The elongation is unmistakable, smooth at one end, uneven at the other, with a length-to-width ratio estimated to be at least 3:1. This shape has puzzled everyone studying it, including specialists in cometary structure like Karen Meach, whose work on 1I Oumuamua set the precedent for analyzing such faint signals. If it were a normal comet, we'd expect a rounded head and a tapering tail. This is different. The frame shows a body that seems evenly stretched, almost like a cylinder. The brightness peaks slightly toward one side, suggesting it might be spinning rapidly on a 7 to 9 hour rotation period, blurring its features the way a long shutter smooths moving water. The faint light we see isn't emission, it's reflection scattered through a thin layer of ejected material, too tenuous to be called a proper coma. This object's form is defined more by its interaction with light than by its physical boundaries. The shape stands as a physical clue wrapped in uncertainty geometry without a surface.
The absence of color.
What can a lack of color tell us about an object's past? When astronomers processed the raw images of 3I Atlas, they found something curious: no real color. Most comets show at least a hint of tone, like a greenish halo from cyanogen gas. But this object gives almost nothing. Across visible wavelengths from 400 to 900 nanometers, its spectrum flattens into a neutral gray. As planetary scientist Alan Fitzsimmons has explained with similar objects, this absence tells us 3I Atlas isn't actively outgassing in any strong way. Instead, we are seeing pure reflection bouncing off a surface so dark it has an albedo, or reflectivity, of only 2 to 3%, literally blacker than asphalt. Over millions of years drifting between stars, its surface has been bombarded by cosmic rays, baking carbon molecules into complex dark organics called tholins. These materials absorb almost every wavelength of light, combining into a neutral gray when seen from a distance. A slight rise in the infrared spectrum suggests the presence of carbon dioxide ice just below the crust, but the signal is incredibly weak. For an interstellar object, that lack of vibrancy isn't emptiness. It's age, a testament to an eons-long journey through the void. This is the color of endurance.
Edge of certainty.
How do you prove something exists when it's barely even there? 3I Atlas lives right on the border of what our detectors can prove. In its raw data, the comet is a whisper above background noise, with a signal-to-noise ratio barely clearing the 3 sigma statistical threshold required for a confirmed detection. but as astronomer David Jewett, a pioneer in discovering faint objects in the Kuiper belt, would confirm, the difference between random static and a real object is consistency. Real light behaves with intent. It repeats and holds a pattern where chaos can't. That's what makes the 3I Atlas image meaningful. Across exposures, the faint streak appears in the exact same coordinates predicted by orbital models, delivering just a few dozen photons per minute to the detector. Its brightness curve remains stable despite atmospheric shifts and thermal noise from the camera itself. The data isn't just faint, it's fragile, requiring mathematical reconstruction to separate the comet's photons from random ones. This process, called image stacking, is less like taking a picture and more like building one from scratch over hours of observation. The final image exists only after millions of calculations reduce chaos into geometry. It's an image at the threshold of certainty, not sharp enough for comfort, but too consistent to dismiss.
Refusing form.
What happens when your discovery refuses to be discovered? Once the image of 3I Atlas was assembled, it didn't behave like anything the calibration software was designed for. Algorithms that measure coma, nucleus and tail couldn't settle on a pattern. The numbers diverged. In data terms, that means the target is either unstable, or the physics behind it doesn't fit our templates. As interstellar object expert Matthew Knight has noted in his research, these visitors often challenge our models. 3I Atlas breaks the logic. Its confirmed hyperbolic orbit, with an eccentricity of roughly 1.1, proves it's not from around here. It behaves like something between 1I Oumuamua, which had no visible coma, and 2I Borisov, which displayed a textbook coma even at 3 astronomical units from the Sun. Its blur is too diffuse to be a solid asteroid but too clean to be an active comet. That ambiguity makes classification nearly impossible using standard cometary models. The picture isn't wrong, it's just showing us a kind of object our instruments and our scientific language weren't built to categorize. It exists in a scientific gray area.
Mathematics of blur.
When an image can't explain itself, how do you make it talk? Mathematics takes over. The frame of 3I Atlas is too faint for traditional analysis, so scientists like Robert Warwick, the discoverer of Oumuamua, turned to numbers to extract what the light couldn't say. Every pixel becomes a coordinate, every shade of gray, a probability. The first step is motion modeling through precise astrometry. Plotting its position across nights confirms its hyperbolic trajectory and its 12 kilometers per second velocity. The math is certain. It's moving too fast to ever be captured by our sun. Next comes brightness fitting, or photometry. The faint gradient along its length is modeled to estimate its shape and rotation. Simulations show that if the nucleus is elongated with a 3-to-1 ratio, a slow tumble could recreate the uneven brightness we see. The math detects a tiny variation the eye can't. Even the blur itself becomes measurable through a process called deconvolution, which mathematically reverses the distortions, separating motion blur from its intrinsic shape. The image shows uncertainty, but the equations describe exactly why it must look that way.
Distortion or discovery.
Is that a real shape, or just a ghost in the machine? Every astronomical image has them. Cosmic rays can leave small flares, and tiny tracking errors can accumulate and masquerade as structure. When the first image of 3I Atlas was released, that question appeared immediately. How much is the comet, and how much is the instrument? The cylindrical blur could, in part, be a subtle elongation caused by the camera compensating for motion and noise, an effect related to the telescope's point spread function. A residual drift of just half a pixel per exposure, when multiplied by dozens of frames, creates a false extension. But not all anomalies vanish under scrutiny. As astronomer Wesley Fraser has explored in his work, consistency is key. When the images were independently processed using different software, the same general elongation remained. The angle of tilt and brightness gradient persisted. That argues against coincidence. If distortion were the only cause, its signature would shift between instruments or processing techniques. Instead, the shape repeated itself, asserting its bizarre geometry through the limits of our observation.
Escaping definition.
At some point, what do you call something that refuses to be named? The discussion around 3I Atlas stopped being about what it looked like and became about what it refused to be. It wasn't a traditional comet, lacking a tail. It wasn't an asteroid. Its light curve was just too smooth and its spectrum too neutral. It presented something in between, a blur that really resisted interpretation. The data, which experts like Amy Mainzer from NASA's NEOWISE mission used to classify thousands of small bodies, paints a picture of contradiction. The brightness curve, varying by less than 10%, suggests a single, stable body, yet its slight asymmetry hints at a slow tumble, or maybe, just maybe, fragments orbiting a shared center. Its trajectory confirms an interstellar origin, a path that ensures it will never return. That certainty of escape is the only familiar thing about it. It forces us to confront the uncomfortable idea that seeing isn't the same as knowing. Sometimes the clearest image possible is one that stubbornly refuses to resolve. It challenges not just our technology, but our very system of classification.
Between categories.
So, if it defies every category we have, what could it be? This is where scientific observation meets informed imagination. 3. I Atlas sits perfectly between the two prior interstellar visitors. 1I Oumuamua was sharp and fast. 2I Borisov was almost too typical. 3I Atlas is neither, behaving like a memory of both. It's too diffuse to be solid rock, too clean to be a classic comet. It exists in a gap where our definitions just fail. It's objects like this that inspire radical new ideas. When data stops fitting patterns, thinkers like Avi Loeb have argued that we must be open to unconventional explanations. While he was referring to Oumuamua, the principle applies here. Is this a new type of dark comet that outgasses materials our instruments can't detect? Could it be a fragment from a tidally disrupted exoplanet, an entirely different class of object? Is it 90% asteroid and 10% comet, or something else entirely? The object is a scientific mystery box. The blur is both evidence and absence, a confirmed detection that withholds its identity, reminding us that our categories are only conveniences, not cosmic truths.
Measured by blur.
What is the final story of a visitor we only glimpse as it leaves forever? When the light from 3I Atlas fades from our view, the photograph will remain, a faint smear in an archive. In most sciences, this would be dismissed as inconclusive. In astronomy, it becomes the most honest evidence possible. As astrophysicist Gregory Laughlin might agree, a blur is what happens when the scale of the universe meets the limits of our focus. Everything measurable about 3I Atlas, its speed, its path, its rotation, its chemical hints, exists inside that faint streak. Its weakness is its strength. It forces meaning to come from physics and mathematics rather than from simple appearance. Soon, it will leave our system entirely, receding back into the interstellar dark. The blur we have is not the beginning of a study but the end of accessibility. It's not a picture of a destination, it's a snapshot of passage. It is a faint fingerprint left on the window of our solar system by a traveler just passing through. 3I Atlas was never truly seen. It was measured by its blur, and that is the clearest image we could ever hope for. 3I Atlas is a visitor that escapes our definitions, a blur that exists in the thin space between what we know and what we can only imagine. What do you think is hiding within that faint smear of light? Share your theories in the comments section below. We're always curious to hear what you think. If you want to continue exploring the universe's greatest unsolved puzzles with us, don't forget to like, subscribe, and hit the bell icon so you won't miss our next deep dive. Thank you for watching Sci and Why.